Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to discuss it's called the definite integral and how they're evaluated. So before we get right into it, I want to start by just talking about grocery shopping, believe it or not. So imagine you're going to the grocery store and we end up with, say, 3 different bags of things. And imagine that these bags, each bag has got the same item, which I'm just going to represent with these different geometries here. Now, if we think about the total amount of money that we're going to spend here, whatever these items are, they have a cost. There's a certain amount of dollar per item, and then we multiply by the number that we purchased. And the cost per item times n, the number that we purchase, would represent the increase in cost due to whatever's in this bag. Over here, this stuff has perhaps a different cost per item. Oops. And then we would multiply that by the number of things in this bag, and then this product would give us the total amount of money represented by what's sitting in here. And same thing over here. Whatever these rectangles are, they cost a certain amount per item. So I'm dollar per n. And then if we multiply by the number, we would get the total cost of the items in this bag. If we add these all up, we would get the total cost of the stuff that we're purchasing in the bag. So I just want to kind of conceptually realize that it's cost per item times n, how much is there, plus cost per item times n, how much is there, plus cost per item times n, how much is there. Now, over on the left, we're going to consider some sort of function here, f of x, and just talk about what happens as we go from the point a, f of a, to the point b, f of b. The difference between these two, f of b and f of a, depends, is a reflection of what happens as we move along this curve. If I pick a spot on this curve, like right here, that spot has a certain slope. Right? It has a tangent line that maybe looks something like this. I'm going to go ahead and write this in red. And if I think about what happens to the function as I move along this point here, there's going to be some sort of change in f as we move from left to right. And that change in function value can be estimated by the rate at which f is changing, which is change in f over change in x, and then multiplying by my change in x. That's pretty much the same thing as what's happening over here. We have a certain dollar per unit item times the number of items. Dollar per unit item times the number of items. Well, this is basically the same type of equation here. F is changing at a certain rate. That's very similar to the cost per item. The total bill is changing at a certain rate. Then when we multiply by the number of items, we get the change in cost associated with this, whatever's in this bag. Over here, if we take the rate at which f is changing and multiply by change in x, we're getting an estimate to the change in f. Now, f of b, whatever it is, it has to equal f of a plus the total change in f as we go from a to b along this curve. The total change in f is the sum from I equals 1 to n of this expression, delta f over delta x times delta x. Now, this expression right here really is an estimate for the change in f, depending on n, how many subintervals we would break this up into. So now, at this point, if you're in my calculus class, we know that we have a limit for dealing with things like this. We can make this estimate perfect by driving n to infinity. So I'm going to rewrite this, and I'm actually going to rewrite it by moving this to the left and putting a limit in front of this. So what we have is limit as n goes to infinity of the sum from I equals 1 to n, delta f over delta x times delta x equals f of b minus f of a. Now, as n goes to infinity, this sum becomes infinite. This becomes a df, a dx, and this becomes a dx. If we have an infinite number of rectangles, that becomes infinitely small, this becomes infinitely small, this becomes infinitely small. And this is what the integral is. So this now reads the integral df dx times dx equals f of b minus f of a. And this integral is from a to b, and the a and the b we call limits. And as far as the symbol is concerned, the a is the lower limit, it typically goes here. The b is the upper limit, it typically goes here. Now, usually when you see this equation in textbooks, it's not written quite like this. It's usually written like this. And this equation is basically a corollary to what's called the fundamental theorem of calculus. And I'm going to save the fundamental theorem of calculus for another video here, just talk about this. This equation is typically used to evaluate integrals. So what this is saying is integral a to b f of x dx is equal to f of b minus f of a. And again, this is true provided that this is the derivative of this function. Or another way to say that, f of x would then be the antiderivative of this function. Right? So this is called the definite integral. This is how it's evaluated, by taking f of b minus f of a. And again, provided that this function, capital F here, is the antiderivative of this function. So what I'm going to do here, I think I'm going to go ahead and just stop this video now and go through examples in a separate video. Everybody have a great day.